You can't see the flame, but it's burning vigorously. And it delivers the energy where you need it. These vehicles all have one thing in common. They're running on a fuel that may one day replace the gasoline we're using up so fast. These tractors, cars, and buses all run on hydrogen. It's nothing to do with the hydrogen bomb. This is just a chemical that burns like any other fuel, but with one special advantage. It's the main constituent of water, H2O.
The only thing that runs out when you use hydrogen is water, and there's plenty of that. So it can go on forever. We don't have to worry anymore.
A cylinder of hydrogen gas is just a way of storing or transmitting energy.
Bring up the RPM.
And when you burn it, all you get is water. Our present energy problems are caused by our dependence on imported fossil fuels. But you can make hydrogen using almost any source of energy, nuclear, fossil, or renewable, and water.
Well, it can go on forever. It's a perpetual fuel. And provided you have an energy source which can go on forever, and I think nuclear and solar are the examples that I have in mind, we can't put a nuclear plant in everyone's house or in everyone's car. And so it's very difficult to use that perpetual energy source ourselves personally. But we can bridge from nuclear and solar plants to our households and our automobiles and our airplanes by using hydrogen.
It means that if our children wish, in a world without petroleum or natural gas, other primary sources of energy can be turned into hydrogen to power their transportation. But for every silver lining, someone seems to find a cloud. Why, for example, in a town where they make hydrogen cars, did they name this street after a disaster? Launched in 1936, built for German national prestige and to link the fatherland with the Americas, the Hindenburg was a wonder of the skies, the world's greatest airship. Diesel fuel ran the engines, but huge bags of hydrogen gas held its fragile structure aloft. On the 6th of May, 1937, the great airship reached New York, intending to inaugurate a new era in fast and luxurious transatlantic travel. On board were 35 passengers and 61 crew. To greet them, the newsreel cameras were out in force, and one particular radio reporter, Herbert Morrison.
The ship is no doubt busting with activities. We can see the passenger probably lining the windows looking down at the field ahead of them. It's practically standing still now. The back motors of the ship are just holding it just enough to keep it from bursting into place.
Get it started. It's fighting, and it's crashing. It's crashing terrible.
And it's falling on the morning fast, and all the folks between us. This is terrible. This is one of the worst catastrophes in the world. Oh, it's a terrific crash, ladies and gentlemen. The smoke and the flames now. Oh, the humanity and all the passengers screaming around it. I can't talk, ladies and gentlemen. Honest, it's just laying there, massive smoking wreckage. And everybody killed. I'm going to step inside where I cannot see it. I've lost my voice. This is the worst thing I've ever witnessed.
A gas leak and an accidental spark, or sabotage? Whatever the cause, the Hindenburg has left a cloud that still hangs over the men who would like to bring hydrogen back into our lives. It's a public acceptance problem. How do they handle what they call the Hindenburg syndrome? Hydrogen engineer and businessman Roger Billings.
As you can see, we're taking this problem head on. Hindenburg Lane is the name of the street where the first hydrogen village is being built.
And at the Institute of Gas Technology in Chicago, this is Derek Gregory.
Yes, a group of hydrogen enthusiasts a few years ago got together over dinner one night, and we said we have to protect hydrogen from this slanderous attack about being too dangerous to use. We formed a society for its protection, and we called it the Hindenburg Society. Nothing like leading with the chin. Our Hindenburg has a little 2 after the H to distinguish it from the airship.
Given the choice of that disaster or a similar fire in one of today's planes, which would give you the better chance of survival? From Lockheed, Willis Hawkins.
I'll take hydrogen.
Lockheed California proposes a hydrogen-powered jumbo jet. But is that safe after the Hindenburg?
The fact of the matter was that Hindenburg had 97 souls on board, and maybe 100 or 200 underneath it. And when you look at the pictures, most of the people got killed because they jumped out of the thing. The hydrogen went up and away from the accident. And the people that were burned from the diesel fuel that was ignited, not the hydrogen.
In fact, the survival figures are remarkable. Of 97 passengers and crew, 62 escaped with their lives. Only 35 were killed, including one on the ground. Why? Fuel consultant Bill Escher.
Well, 2/3 of the people actually survived that disaster because of the forgiving nature of hydrogen vis-a-vis, say, gasoline or something like that. Hydrogen, when it's on fire, burns upward. It burns with a non-luminous flame, and it is essentially a safer material than some of the fuels that we use today.
We decided to check on that for ourselves with the help of scientists at the Denver Research Institute. First, gasoline. In each test, there'll be a flame burning nearby, ready to ignite any fuel that spills. For that job, they chose hydrogen itself. You can't see its flames, nor will you feel much radiant heat around it, but you'd certainly feel it if you touched it. Now for the first test. A bullet into the can of gasoline. Scientist and marksman Frank Lynch.
Okay, go ahead, Frank. The gasoline is being distributed over a fairly wide area. The explosion carried it quite a distance.
Gasoline is a carbon-based fossil fuel, and carbon means a lot of radiant heat. In a big fire, that alone could fry you. Here's a second carbon-based fuel that's widely used today, propane gas. What makes this so useful is that you can store it as a liquid at ordinary temperatures, in a can.
Hey, that's right. More like it. And it's your left scene. We have a bush problem.
Now for hydrogen. This cylinder is larger, but it contains about the same amount of energy as the others. It holds it in a very curious form. The cylinder contains metal of a kind that readily absorbs hydrogen and equally easily gives it up. The cars and buses we saw earlier were using this kind of storage. That's the hydrogen gas escaping through the hole. Just the gas. It hasn't yet caught fire. And there it goes. Throughout this film, we'll keep safety firmly in mind, but it's really not the major problem. The real difficulty is simply that this is more expensive than oil or natural gas that comes out of the ground. You have to make hydrogen. At the Brookhaven National Laboratory, Frank Salzano.
In comparing hydrogen to natural gas is itself a source of energy as well as being an energy transmission distribution medium. In the case of hydrogen, since it doesn't occur naturally, obviously the hydrogen has to be derived from some primary source of energy. The advantage that you have with hydrogen is that you can derive it from many different primary sources of energy. It can be derived from coal, it can be derived from natural gas itself, it can be derived from solar, it can be derived from wind, it can be derived from hydroelectric energy. Almost any source of energy that can be converted to electricity can be used to manufacture hydrogen.
This is electrolysis, splitting water, and it's our first way of making hydrogen. Given the electricity, it should be a very efficient method of energy conversion. But the reactions are slow unless you have electrodes of a noble metal, such as gold or platinum. So it's been a cumbersome and expensive process, until the invention of what Len Nuttall of General Electric calls a solid polymer electrolyte.
The solid polymer electrolyte is a sheet of plastic, as the name implies. It's a thin film of plastic that serves as both an electrolyte and a separator for the two gases from the hydrogen and oxygen, which are generated on opposite sides of the electrolyte. This is the electrolyte itself. In its finished form, we have a thin film of catalyst pressed on either side, which is shown on this finished, what we call a membrane electrode assembly. And this is the heart of the cell. It brings the cost, of course, down considerably by reducing the cost of noble metals, and by being able to operate at high current densities, we're able to get the cost of all of the other materials used in the cells down considerably, so that it makes water electrolysis much more attractive as a means of generating hydrogen as compared to some of the alternate forms that are being used at the present time.
It still doesn't look all that cheap. And it requires more testing.
So we have about a week's worth of tests, and then we'll expand to 12 cells.
What current density have you been operating?
It's a 50 kilowatt test cell. That's the power for 50 individual electric heaters. A lot of energy goes into a very small pipe to carry the hydrogen away. But this is only a baby. To build a small power conversion plant, you'd multiply this by 1,000 or more. Stacking them like sliced bread, you could generate vast quantities of hydrogen in remote places like the Canadian North. And the source doesn't have to be continuous. A plant like this should pay for itself, running for as little as 30% of the time. So you could also build them to use up spare off-peak electricity. In France, in the next 10 years or so, they'll have off-peak nuclear electricity in abundance. The French will probably turn that into hydrogen. But do you have to make electricity first? Over the border at a research station in Germany, they think not. This is probably the safest kind of nuclear power reactor yet developed, and in its use of heat, by far the most efficient. The father of the pebble bed high-temperature reactor, as it's called, is Rudolf Scholten.
The main difference is the use of this type of fuel element, which can operate at 1800 Fahrenheit. The temperature 2 times or 3 times higher than in other reactors. This fuel element, which seems to be black, and the real operation will be a red or even white, and this high temperature level. White, hot.
It's been running for 10 years at nearly 1,800 degrees. Cesar Marchetti is interested in high temperatures because he can use them for an ingenious second method of splitting water. He developed it at a Euratom research facility near Milan. Here, a small furnace represents the source of nuclear heat. And here's the other raw ingredient, water. But in addition to this, you also need a great deal of plumbing and several chemicals, because even 1,800 degrees isn't enough on its own. If you wanted to split the water that's entering here with just heat, you'd need over 5,000 degrees, and you still wouldn't have separated the oxygen and hydrogen gases. So here's the trick. In this column, they combine the water with chemicals to make a mixture of acids, which can be separated to go in 2 different directions. Going to the right, they have the chemical that took oxygen from the water, and that's what they put in their furnace, where it's broken up by the heat and where the oxygen is released. The other acid took up the hydrogen, and that goes to the left. In this particular process, it's fed to an electrolytic cell, but some other chemical systems use heat on this side, too. But it all goes around and around, and the hydrogen comes out here. Everything else goes back to the starting point. The chemicals, in this case sulfur dioxide and bromine, are used over again. It's a very efficient way of using energy, but is it cheaper than ordinary electrolysis? According to Marchetti, this, in combination with the high-temperature reactor, should be cheaper than a plant to generate nuclear electricity. And the record shows that chemical engineering of this kind can be scaled up quickly, so this or some other chemical cycle could turn out to be the cheapest way of making hydrogen. It simply pours out, but in practice there's a problem. Not everybody would like the idea of their clean hydrogen coming from what many see as dirty, radioactive, waste-producing nuclear power stations. Caesar Marchetti.
Well, hydrogen makes possible to bring the nuclear system very far away from the inhabited areas and bring at the level of the inhabited areas something which is extremely clean. And so what people see is it's very clean, and the dirty job is it's somewhere in the world, but very far from inhabited areas.
For Japan, there are plans for nuclear reactors on artificial islands. They generate both electricity and hydrogen going into a marine pipeline. Are the Japanese really serious about that?
Well, they look enthusiastic. I mean, I see their eyes shining.
But currently, Germany has the nuclear lead. They're building a 300-megawatt high-temperature reactor. But for those who still don't like nuclear, try this. Solar power is politically popular, and it's an ever-renewable source of primary energy. Here, Sandia Laboratories are evaluating at Livermore the merits of various manufacturers' solar reflectors. How do they stand up to the weather? How does desert dust impair their performance? The idea is to concentrate the sun's rays onto a target where you could use the heat to split water and make hydrogen. The energy source is free, but you could pay a fortune to collect it.
The automatic isn't working.
If solar isn't working yet, it's not for lack of money. For every one research dollar allocated to hydrogen, $40 go into concentrating and collecting sunbeams and to finding ways of using them. In the end, it may prove possible to use the sunlight directly, though as yet it looks like a long shot.
Now we're taking the cover off of the light source and exposing the blue rhodium-containing solution to simulate sunlight.
The water has a complex blue chemical dissolved in it. Harry Gray from Caltech.
At the moment it's absorbing sunlight, and hydrogen gas is building up in the solution, and bubbles of hydrogen gas should come out of the cell.
At the Jet Propulsion Laboratory, Ami Gupta.
This has a color that makes it absorb about half of the solar spectrum, which means that it does a very good job of collecting sunlight reaching the Earth.
I think the efficiency now is quite respectable. It's 5% of the sunlight is converted into hydrogen gas. Our research is aimed at upping this efficiency to 15 to 20%.
Their present chemical is ingenious, but won't do that. And it's expensive.
It's a long shot at the moment, but it's a very important long shot, because if it comes in, it will allow us to convert solar energy just using simple chemicals and just water as the source of hydrogen. It is a long shot, but it's an extremely important one in my view.
Well, failing all else, it's back to square one, coal. In the short term, this will be the simplest method. Burn coal with steam, as in the old town gas plants, and you get hydrogen, along with some unpleasant byproducts. We could improve on that today, as we could on the delivery of hydrogen gas. Right now, we're down to this. a gasoline-fueled truck. Hydrogen, pressurized to 2,500 pounds per square inch. To contain that pressure, the cylinders must be enormously heavy. But even so, you're not moving enough gas to think of it as a useful fuel. You'd need far too many deliveries. It would be far better to use a pipeline, such as this one being installed for natural gas. To contain the high pressure, 1,000 pounds per square inch, these pipes have been made stronger than some that were tested to destruction. The gas industry would not release their test film, but this is what we understand happens in what's called a brittle fracture. Pipelines are now designed in such a way that this, they say, can't happen. But what if they were used for hydrogen?
Well, if we convert to hydrogen, we believe that we can use those systems on pure hydrogen. But we have to find out if that belief, that assumption is correct. There could be some problems with embrittlement of steels in the pipeline. Hydrogen can get into the structure of steel and gets in between the atoms, between the molecules in effect, and causes the steel to become brittle. And then it can fracture very easily.
Would the effects of hydrogen embrittlement be more severe on the kinds of flaws which pipelines contain? At Sandia Laboratories, Steve Robinson.
What we have here is a machined flaw, which is intended to behave like a flaw which might be accidentally put into a piece of pipe during manufacture, and which might escape detection and actually be put into a pipe.
It's welded into the jacket to contain any leak. It will carry concentrated energy. In fact, these high-pressure pipes do the same job as the high-voltage electricity cables that march across the countryside. But the pipeline does it less obviously and a great deal more efficiently. They calculate that if you run it at the same pressure, say 1,000 pounds per square inch, you can transmit the same amount of energy whether the pipe's carrying natural gas or hydrogen, provided it stays there. When the pressure is turned on, what happens? Well, in a year of such tests, the answer is not very much, which is good news so far.
The other part of the job is to find out how much the hydrogen degrades the performance of the pipe. So we simply blow them up with hydrogen. Well, after our first year of testing, our first conclusions are that at typical pipeline pressures of 750 to 1,000 psi, if you were to use hydrogen instead of natural gas, you might have to reduce that pressure by about 15% to have the same degree of safety.
Which is not a great loss. At the city gate, as it's called, the pressure is in any case brought right down to just a little above atmospheric, and it now passes into a vast assortment of pipes, joints, and other components. At the Institute of Gas Technology, Derek Gregory.
In the distribution system, low pressures, we don't worry about embrittlement, but we worry about leakage. And the hydrogen will leak out of a small hole or crack at about 3 times the rate that natural gas leaks out.
That's what the theory says. To test it out, they put together a plumber's nightmare of bits and pieces, most of them manufactured for use with natural gas. They're not made perfectly, they're made for a price. There'll always be a little leakage, and over a whole city, that's not only a matter of safety margins, but also a question of how much energy disappears out of the system. The study confirms the theory. 3 times the volume escapes, but that amounts to almost exactly the same energy loss as with natural gas. So you break even. Conversion to hydrogen, they say, is feasible. Your house could one day be running on hydrogen. And this, says Roger Billings of Utah, is the world's first hydrogen homestead. There are still a few hitches. As we prepared to film Tanya Billings, Roger struggled unsuccessfully to demonstrate a hydrogen-burning simulated log fire. We got the impression that some of the equipment didn't get a lot of use, perhaps because current methods of producing hydrogen and its delivery by gas cylinder make it so expensive to use. But if they can't yet demonstrate the economics, the Billings can at least refine the equipment. Hydrogen ignites differently, and it would need an additive to color that near-invisible flame. To sort out the problems will take patience and also money. Here, baking muffins is a serious matter. It's part of the process of turning hydrogen into a business proposition.
They look good. Can I try one? Yeah. Hot. How about a little butter on it?
Tonya and Roger Billings are in on the ground floor of what could become one of the world's greatest growth industries.
An advantage of a hydrogen home is that with the moisture content in hydrogen combustion, the food comes out very moist and very tasty. Of course, the disadvantage is that a lot of the equipment is still being worked out. Having the first one in the world, we have a few of the little prototype problems that we're still perfecting, but it works pretty good. So, try one.
We did, and there's nothing wrong with hydrogen cooking. Where will Roger Billings take his ideas from here?
This is the first project of what we hope will be many. It's a hydrogen-powered home, and from the technology and the experience we gain here, we plan to operate 35 homes here in the vicinity on hydrogen. And then in a year and a half, we hope to break ground on a coal gasification plant, which will provide the hydrogen to convert the whole city of Forest City, Iowa.
So perhaps Roger Billings and his construction projects will give us a chance to judge the domestic side of what is called the hydrogen economy. Among the vineyards of California, hydrogen is already with us. They've been making it for years and storing it here, not as a gas, but as a liquid. You can buy a few tons anytime you like. Its availability is a legacy from space. It was not used for the Saturn V rocket that launched Apollo, but it was used in the two upper stages that had to be as light as they could possibly be made, including the fuel. For a given thrust, the lightest they could find was liquid hydrogen, so hydrogen carried man to the moon. It was mainly for the space program that 3 companies built a plant, each capable of producing up to 30 tons of liquid hydrogen a day. They use natural gas as their starting point and pass steam into its flames in this reactor. Out comes carbon dioxide. That goes to make fizzy drinks. And the hydrogen. The hydrogen is purified, then goes downstream to the liquefying plant. There's a penalty here. To cool it uses energy, and that adds to the cost. But for your money, you take away a remarkable liquid. This will show how cold it is now. As they fill a road tanker, the hydrogen gas in the space above is vented through this pipe, and air touching that gas pipe is itself instantly liquefied. The liquid hydrogen is far colder, so that's carried to the customer in an insulated container, like a giant thermos bottle on wheels. One truck contains less than 1/3 of the energy in a comparable gasoline tank truck, so it's more expensive to transport by road. You'd need 3 times as many trucks. But for safety, it may have an edge. As a product of the space age, liquid hydrogen is subject to elaborate safety codes. Yet ways have been found to send it by rail without anyone having to travel with it. Carrying 8 tons of the liquid, this is one of a fleet of tank cars to be found any day somewhere on this route. 5 to 7 days, no tunnels, and today's shipment arrives at McCook, just outside Chicago. As the gas pressure built up on the way, hydrogen was vented automatically, mixing the gas with enough air to make it harmless. For over a decade, the safety record has been excellent. And if it can travel safely by rail, maybe hydrogen could also power the locomotive. fuel technology consultant Bill Escher.
We have looked at hydrogen for the powering of diesel-electric locomotive, actually a vintage locomotive that's been converted to hydrogen in a model form. We show a model of a liquid hydrogen tank, of which 4 exist. We show an engineering support car for the development phase of operation. Then you unveil the train to the traveling public and to the rail companies themselves. We would have basically 2 cars, the locomotive and the ancillary car carrying the liquid hydrogen. The liquid hydrogen takes approximately 3 to 4 times the volume that the diesel fuel takes that it's trying to replace. That would be step 2. Then finally, you have to make a special design of the locomotive, and that would be step 3. That step would in fact require fundamentally a redesign and a rethinking of the modern locomotive. But in Canada, and in the United States, and in Mexico, there's almost zero electrification, and yet we have this full dependency on oil-based petroleum. So I think it's going to be North America where this will first be attempted.
For aircraft, they've been looking at liquid hydrogen since the 1950s, when the Lockheed Company had a contract to design a plane for the U.S. Air Force. The project was canceled, but they'd already started testing the fuel for safety. Liquid hydrogen burns fast, but without the shock of an explosion. But the Air Force continued to take an interest. An armor-piercing incendiary bullet will go into, on the left, a gasoline tank, and on the right, liquid hydrogen goes up and away. Again in slow motion. Protection from the heat could be with the thinnest sheet of aluminum. Suppose a ruptured tank were struck by lightning. No great explosion, and like the Apollo capsule, such a plane would be lighter. Its performance would be up. What about passenger airplanes? The rest of us would travel in this. It's a new kind of big jet proposed by Dan Brewer and Lockheed California President Willis Hawkins.
Collaborating.
It would carry 400 passengers from Tokyo to New York, and it would cut the weight of fuel dramatically.
Approximately 26.5 tons of liquid hydrogen are required for that mission. The equivalent Jet A fueled airplane would require 82.5 tons of aviation-grade kerosene.
But liquid hydrogen is a lot more expensive.
Hydrogen really becomes important when we have come to the place where the scarcity of petroleum fuel is such that its price is very high, or we're forced to make synthetic petroleum, in which case the hydrogen really becomes competitive.
That still seems a long way off. They recognize that nobody's going to pay for a major new design right now. So here's a fallback position. It's based on the kerosene-powered planes they're building today. What changes would you have to make to fly one of these on hydrogen? First, look at the engines. This, it seems, would be the easy part, because hydrogen burns much faster and more evenly. It also radiates less heat to the metal around it. Dan Brewer.
An engine like this would burn beautifully on liquid hydrogen. The combustion chamber would be about half as long as it is now with Jet A fuel. Would add a heat exchanger in the core exhaust, wind up with none of this very black soot.
A bigger change would be in the wing. Look inside one. In current aircraft, the wings are the fuel tanks. Crammed full of kerosene, they're so heavy at takeoff that they actually have to build the wings bigger to generate enough lift to get it all off the ground. The much bulkier liquid hydrogen wouldn't fit in here. Could you put it in the body of the plane with the crew and the payload? How much space would that take?
The liquid hydrogen tanks would start about here. The 2 tanks together would occupy about 40 feet moving forward and would end the equivalent of about here. Liquid hydrogen is very low density, but it's about 1/3 the weight of aviation-grade kerosene.
A lot of space. But putting it in here is their answer. To modify an L-1011, they'd extend it by 40 feet and slot in 2 extra sections for the tanks. The proposal is to build 4 such aircraft and fly cargo to prove the idea works. This route could start, they suggest, from Pittsburgh. It could cross the Atlantic to Birmingham, England, then fly on to Riyadh in Saudi Arabia, and back via Frankfurt. Why those particular places? Because there's coal to make the hydrogen near 3 of them. Natural gas is going to waste at the 4th. And there should be plenty of cargo to shift. And the cost?
Our first estimates are that it'll probably cost us somewhere between $1.2 to $1.5 billion. We think that probably half of that is the airplane and 1 of the airports, and the other half of the other 3 airports.
So who pays?
We've actually suggested that the United States take up the problem of converting the airplane and the 1 airport, and that the other countries pick up the operations at the other airports to produce the hydrogen and be prepared for handling it.
If the economics of a subsonic hydrogen transport are marginal, for supersonic flight they would be a vast improvement on the Concorde. The reduced fuel load would give a realistic payload and a greater range. On the ground, the economics are as yet much poorer. Hydrogen energy currently costs about 4 times that of gasoline. Yet, when we were filming, the shares in the With Profits Public Corporation run by Roger Billings were doing well. While still at school, he won an international prize for his work. He got it for a lawnmower.
The little lawnmower engine running on hydrogen, to me, was the culmination of many years of hard work. And I remember running down the stairs and calling everybody I knew to tell them, it worked, I'm rich, it worked. The following day for breakfast, I discussed with my father the need for a vehicle to experiment on now that I had a lawnmower engine running. And my father had just purchased a brand new Chevrolet that he was very proud of. And I said, this is your opportunity, Dad, to be a very famous person assisting science by donating your new automobile. And he just couldn't be convinced that experiment should take place. So the next day at school, I convinced one of my fellow students who had a little Volkswagen that this is his chance to carve out a place in history by letting me use his car. And that night after school, we backed it up on the steps of the school, and I started converting the car to hydrogen. And someone tipped off my father, who arrived and said, what are you doing? And I said, I'm converting this car to hydrogen. And he said, if you've got to blow up a car, blow up my old Model A. Within 3 days, the Model A was running on hydrogen, a little bit crudely, but at least it was running.
Not knowing that undergraduates don't do research, he went to Ford for a research grant. He needed just $1,800 to improve car engines, he told them, and they gave it to him.
In the Model A Ford prototype, we stored hydrogen in large compressed gas cylinders that in fact filled the whole back end of the vehicle. And with all those very heavy cylinders, the car would only go about 10 miles range. But it got the experiments going. From the Model A, we moved on into a cryogenic, or a liquid hydrogen storage system that give us substantial driving range, but had the problem that the liquid hydrogen is much more expensive, and furthermore, it's quite dangerous. I think we demonstrated that. One day we had our liquid hydrogen car at home in storage overnight, and early in the morning we heard a lot of commotion out in front and looked out the window, and here's the whole hydrogen car on fire, spontaneously igniting as a result of a malfunction of the very complex liquid hydrogen system. From that experience, we saw the real necessity to go to the metal hydride storage technique, as we have installed in the Granville, the first car in the whole world to ever run successfully on hydrogen stored in the safe metal hydride form.
Billings heard that at Brookhaven they'd been working with an alloy of iron and titanium, which has the curious property of combining with the gas as though hydrogen too were a metal. Pump it in and it absorbs the hydrogen, giving off heat. making what's called a metal hydride. To recover the hydrogen, pull out the plug. The hydride now cools down, so to maintain the flow, warm it a little with the coolant from the engine. Actual hydride tanks are prepared like this. The alloy is first ground up. This gives increased surface area for hydrogen absorption. Then the grains are enclosed and the hydrogen pumped in. The highest working pressure is usually not more than 300 pounds per square inch, though for experimental purposes it's taken a little higher. How does that compare for safety with the 2,200 pounds per square inch in this hydrogen gas cylinder? First test, knock the top off the gas cylinder.
Pull.
Perhaps that Model A Ford would have gotten further by jet propulsion.
5, 4, 3.
How does the hydride cylinder behave?
Pull. Somebody go there.
The gas pressure is very low. Now the comparison with gasoline. If gasoline had just been invented, there's no doubt we'd make the safety rules tougher. Now for the hydride tank. Still dramatic, but which tank would you prefer to have behind you in the average shootout? Or more likely, a collision? You've had an accident and your car is on fire. This is your gasoline tank and their hydride tank. These two fires started at the same time. The gasoline tank is on the right. Sorry, you lost. The hydride took much more to get it going well. It does burn, especially if you encourage it. But it is relatively safer. A new fuel for widespread use has to be pollution-free, as hydrogen is, except for one small problem. And the cure in a second tank is water. First, the problem. In conventional engines, gasoline and air are mixed, drawn into the cylinder, compressed, and burned. The result is a mixture of unpleasant gases. One type comes from air and the heat of the engine. It makes nitric oxide, acid fumes. This test measures them. Using gasoline, the car is run on rollers and samples taken from the exhaust. High in nitric oxide. Now switch to hydrogen. There's still air going in with the hydrogen, and the flame is still very hot, so you still get nitric oxide. But now with a water injection system, add a little water on every cycle. Down comes the temperature. The efficiency of the engine is unimpaired, and there's virtually no nitric oxide in the exhaust, less than 1% of the quantity before. And Roger Billings holds the patent.
You open the hood, Dave? You see, we've taken a standard Cadillac engine with all of its pollution control equipment. We've got equipment to reduce carbon monoxide, to burn up the hydrocarbons, eliminate the nitric oxide, and all in all, a very expensive, cluttered system to try to save the environment. And for hydrogen, really none of this is necessary, because when the hydrogen burns, the only possible pollutant is nitric oxide, and our water induction system virtually eliminates that. So you have a pollution-free system on hydrogen. Also, you'll notice that it runs a little better. Let's start up on gasoline, and then we'll switch it over to hydrogen. Dave?
It can be run on gasoline for a long journey across country. Then the switch is made to hydrogen in town to cut down air pollution. That idea is being tested in Riverside, California.
Now I can make it. Oh, hello, everybody. What do I say to
At the downwind end of the Los Angeles basin, there may be severe air pollution from road traffic.
Yeah, we have a lot of smog and all. It got worse. When I came here, there was no smog. Not at all.
A local doctor, Bob Zweig, ran a campaign about it.
I think that hydrogen should get started in Riverside because Riverside probably suffers more from air pollution in the air basin than most other communities. If we can demonstrate that this bus will reduce air pollution to the point where it will improve the health of the people living in the air basin, we will be able to use this information to help our legislators encourage more buses like this. And I think that this will bring the price of hydrogen down to where it's competitive with the present gasoline.
One bus. For Bob Zweig, one bus is enough to make his point. It's the old who suffer most from the smog. Now they can join in testing the bus as part of Riverside's free dial-a-ride service. For Roger Billings, this tough daily use will show up any deficiencies in the experimental vehicle. Needless to say, there are some. For one thing, there's a lot of extra metal underneath. How does it drive?
It's a little heavier. Bottom heavy.
And if you push it?
Acceleration is slower. There you go. Number one.
It's a flashback to the carburetor, a timing problem. As with Billings' own Cadillac engine, it will run on either hydrogen or a conventional fuel.
One of the problems with the Cadillac and the other prototypes we've converted is switching the timing. Hydrogen has a much faster flame speed, and so to make the engine run properly, we must retard the time at which we ignite it in the cylinder. And to do this requires some rather difficult changes in the ignition system, so we usually have to compromise and set the timing somewhere in between the two.
For each of the first 10, they'll pay $10,000.
This is the hydrogen storage tank for the vehicle, and this particular tank will store about 400 pounds of hydride, giving the vehicle a range of about 100 miles. Unfortunately, we don't yet have a large distribution network of hydrogen stations, and so the car owner needs a way to refill his tank. And to do that, we've built this device. This is a hydrogen electrolyzer, or more simply stated, a piece of equipment which will be installed at the car owner's home.
The first electrolyzers will also cost $10,000 apiece. When the fuel tank goes in here, the rear suspension has to be strengthened. There's still a problem with extra weight, as with the Riverside bus. The sheer weight of hydrides limits the amount of hydrogen that can be carried, and that limits range. On the tank capacity also depends the time it takes to refuel. One pipe is the hydrogen, the other a coolant, to help the hydride take up as much gas as quickly as possible. This bus can only go 60 to 80 miles, and then has to take up to an hour to refill. The water injection system has to be filled too, but soon the water from the exhaust will simply be recycled. Some problems are more intractable. For example, hydrogen supply would be more complicated than gasoline. So the first applications are likely to be where reducing air pollution is important, or where weight, range, and recharging times are not. For example, this started life as an electric battery-driven car, but it's been converted to hydrogen. By taking out the heavy batteries and putting in the same weight of metal hydride tanks, the range is increased from 30 to 100 miles. In this use, weight is a real advantage. Even a gas cylinder is not too heavy, though in practice this will be replaced by the usual metal hydrides. Here there are also plans to use clean hydrogen for underground mining vehicles. But to get beyond these limited applications, big improvements in range and weight are needed. This could be it. In Stuttgart, Germany, a second generation of hydrogen buses is already being tested. Both Mercedes and Brookhaven have been testing a new alloy that contains 2 parts of magnesium to 1 of nickel. It's much lighter in weight, and in tests like this, they have found that it's an efficient hydrogen absorber. But they hit a problem, or so it seemed at first. Unlike the iron-titanium alloy, this one requires a very much higher temperature to produce the hydrogen. In the vehicle, it's possible to use the hot engine exhaust gases. Here in the lab, they'll use a furnace. This is only a partial solution to the various problems, and the technology itself becomes more complicated. But it works. The weight of metal needed to carry hydrogen is down, and the performance is up. This gradient would be a tough test for the heavy Riverside bus. But this one sails up. In practice, there's a trade-off between improvements in performance, weight, range, and charging time, depending on which is the most important to you. Refueling hydride tanks will never be as fast as filling up with gasoline, but it's getting better. Frank Salzano.
In the case of hydrogen, we think charging times can be gotten into the range of something between 10 or 20 minutes. So in the case of charging a hydrogen hydride fuel system, you're talking about an extended coffee break.
And how pure must that supply be? Current research suggests that hydride alloys will selectively absorb hydrogen and will not be damaged by the impurities present if it were made from coal. If so, coal could be the supply until other sources prove competitive. And there's a free bonus with hydrides, a cooling system that requires virtually no additional energy. The old iron-titanium hydride is still needed to start the engine from cold. So Mercedes have 2 tanks on board. By shifting hydrogen from one tank to the other, they can heat or cool the interior. That's full air conditioning at no extra charge. And there's a final bonus. When the bus gets back to refuel, it releases more heat, which someone else may need. But the range is still limited, less than 200 miles on a full tank. Again, one answer could come from space technology. The Gemini spacecraft converted hydrogen energy to electricity using this device, a fuel cell. This is a development, the reversible fuel cell. In this, an electric power supply, represented in this demonstration by a flashlight battery, is applied to water and splits it on either side of a membrane. This is hydrogen. The fuel cell is being charged with hydrogen and oxygen. Now take away the power supply and replace it with something that uses electricity. Now, as in the Gemini fuel cell, the hydrogen and oxygen recombine to give back the electricity. At the Brookhaven National Laboratory, they think that some of the remaining problems of hydrogen transport could also be solved by the fuel cell. In this one, the hydrogen combines with oxygen from air, making electricity to drive a car. A hydrogen fuel cell is much more efficient than the internal combustion engine, but only with the invention of the solid polymer electrolyte has it become practical and cheap enough to use for transport.
I don't think it makes any difference if we increase the hydrogen flow.
From one cell, the output is small. So there are 16 in this module, and 18 modules give a 10 kilowatt car. Because much less hydrogen is needed, this reduces the weight, and at last promises a range and performance that's not too different from cars today.
Yeah, right.
Of course, we don't have to use hydrogen at all. Instead, when the oil runs out, we could synthesize our gasoline from coal and retain a world dependent on fossil fuels. But that would perpetuate our pollution problems and the ways we have to deal with them. And even then, there's one product of carbon-based fuels that's still to be dealt with: carbon dioxide. A great deal is known about it on Hawaii, where high on the lava fields of Mauna Loa, there's a weather station that for over 20 years has been sampling and measuring the carbon dioxide in the atmosphere. Each summer, the forests absorb it, but each winter it builds up. After smoothing out the annual cycles, there's a steady, inexorable rise. In the late 60s, it seemed to shift into higher gear. The oil crisis may have slowed it a little, but now it's going up as fast as before.
Well, we don't know at this point whether carbon dioxide is going to build up in the atmosphere enough to do damage. If we continue burning the fossil fuels at the present rate, or faster, there are a lot of people who believe that we will get into trouble in about 10 years' time, irreversible trouble, and it'll start raising the temperature of the atmosphere, melting the polar ice caps and all this stuff. Now, we don't know, and we won't have enough data on this for about 10 years, by which time it may be too late. So I foresee that there could be a crash program starting in 10 years' time to cut the rate of fossil fuel burning on a worldwide basis, not just one country. Every country has got to do this together.
For that, hydrogen could be a good option. There are other fuels that could be used. In this film, we looked at the case for just one. But the odds are that whatever we choose, 20 years from now, it won't be cheap.
Hydrogen will never be as cheap as any of the currently available primary sources of energy. Hydrogen will never be as cheap as natural gas. It will never be as cheap as petroleum on a per BTU basis. That's unreasonable to expect. But at least you will have a fuel.